Hello folks, today I have another lesson for you on specific heat capacity and the heat transfer between two objects. So this is again, as it says in the statement, this is about amount of heat that is transferred from one object to another. Now, even though the heat is being transferred from one object to another, the temperature change between the first object and the second object is not the same. And the reason for that is the specific heat capacity of different substances are different. So in other words, they take different amounts of energy to change their temperature by 1 degree Celsius, which is what specific heat capacity is. So the question I have, and I'll write down the question with you, and I'll explain the question as we go along. The question that we're trying here is, it says 235 gram lead ball for which the specific heat capacity they have given us is 0.13 joules per gram degree Celsius. That means it takes 0.13 joules of energy to change the temperature by 1 degree Celsius for 1 gram of lead. And this is at a temperature of 84.4 degrees Celsius is placed in a light calorimeter, of negligible specific heat capacity. In other words, they are saying that the amount of heat absorbed by the calorimeter is negligible, don't have to worry about it, and we are going to be ignoring the change in energy of the calorimeter itself, the hardware itself, the container. But the water that is inside will still change temperature and will have energy absorbed and will have a specific heat capacity, just not the container. So now this calorimeter containing, it says 178 grams of water. Okay, so that's the water that is going to be changing the temperature, absorbing the heat that is being released by the lead ball. Again, no chemical reaction, just physically, just transfer of heat. And this one is at 20.5 degrees Celsius in the beginning. So this is the temperature of the water in the beginning before the ball was added, the lead ball was added to the container. Now, they're asking us to calculate the equilibrium temperature of the system. Calculate the equilibrium temperature, which means the temperature when it becomes the same for the object, the ball, and the water. That is the equilibrium temperature. Equilibrium temperature of the system. In other words, they're looking for the final temperature. All right, so let's look at all the components here. So we have the lead ball, we have the calorimeter which has the water. When we put the hot lead ball into the coffee cup calorimeter, or in this case the light calorimeter, the temperature of the water, which is at 20.5 degrees Celsius, will go up, and the temperature of the lead ball, which is 84.4 degrees Celsius, will go down until the final temperature is reached, in which case the temperature of the lead ball and the temperature of the water is going to be the same. So this is very important to understand what the question is asking. So in this case, the initial temperatures are different for the lead ball and the water, but the final temperature, TF if you want, will be the same for the ball and the water. Once we have established that, now we understand that the lead ball is going to be losing energy. So one of them is going to be losing. So let's say this is Q for the lead ball is equal to negative Q for the calorimeter or the water. Because one is losing, one is gaining, to make this equal, what we can say is lead ball's heat is the same as the opposite of what is happening to the water, negative Q. or you can say heat of the water is negative of what's happening to the lead ball, or negative of the lead ball, which is Q. All right, so once we have that, we can write down our equation and solve right away. So we don't have to do it in pieces, we can just do it together. We have M for lead ball, I'm going to use LB for lead ball, times the specific heat capacity of the lead ball, times the change in temperature of the lead ball, is equal to mass of water, W for water, specific heat capacity for water again, and the change in temperature for the water. So this is going to be our equation. This is what you're going to be plugging in for determining that final temperature. Now, the mass of the lead ball is given to us as 235 grams. So 235 grams, we already have that established up there, and multiplied by the specific heat capacity of the ball, which is 0.13 joules per gram degrees Celsius. So proper units, grams and grams. And the change in temperature. Now, change in temperature is the temperature final, which we don't know, minus initial temperature, which is 84.4. Right. Now, you have to remember that one is the negative of the other, so I'm just going to put the negative sign there. That is important. We have that is equal to the negative sign there, mass of the water, which is 178 grams, times the specific heat capacity of water, which is 4.18 joules per gram degrees Celsius, times the change in temperature of the water, which is TF minus 20.5 degrees Celsius. Okay, so now we have all the variables, all the information already plugged in. Now, this is not the preferred way of solving these questions. I'm going to show you the same calculation again and how it is preferred. This one I'm just showing you to explain how the Q values translate into the equation and how we will be able to solve for the TF. Now, if you see in this equation now, we have one variable, which is TF, and we have one equation. So this is possible way to solve it. So now you can just start rearranging the equation, calculating for TF, and you will get an answer. But the preferred way in math and science is first to rearrange the equation that is provided and then solve for the final answer by plugging in the values. So instead of doing this, so this is one way of doing this. I'm going to highlight this for you. This is one option. Now, if you are not comfortable with algebra and you have difficulty with solving questions in math by rearranging the equation, this is your option. This is one way of solving the question, and you will be able to get the answer by solving this. But the preferred way would be to actually find the equation for TF. So I will continue with the equation from here, from the top. I will continue here, and I will start rearranging the equation and then solving for the answer. So first of all, a mass of the lead ball times the specific capacity of lead ball times, I'm going to put in brackets, TF, which is the final temperature, minus TI for the lead ball. So I'm going to say LB, that is different, that's not the same for both, is equal to negative M for water times the specific heat capacity for the water times the TF, which is the common temperature final, minus TI for the water. Okay, so I have this equation or these equations here, and now what I can do is I can open the brackets. So what I get is M of LB times C of LB times TF minus M of LB C of LB times TI of LB is equal to, and now we have a negative sign here. So what I can do is I can take the negative and flip the signs for the TF and the TW, or I can keep it. So let's just keep this value here. So it will become negative mw times cw times tf, and there's a minus there, and now there's a negative, so minus minus will become plus. It becomes mw times cw times tiw. So this is the expanded form for the heat, and now what we know is we want to isolate for TF. So we will take both the TF values and bring it to the same side. So I'm going to keep the M lead on this side, lead ball, C of LB, and T of F, and I'm going to bring the right hand side's water component with the TF, the final temperature, to the left hand side. So it will become plus MW CW TF, and I'm going to take the lead ball's initial temperature component and take it to the right hand side, and it becomes M of LB, C of LB, Ti of LB, and then M of water, C of water, T initial of water. So you see now the TFs are together and the TI values are on the right hand side. Continuing on with our algebra, we are going to take TF common outside, and what we get is M of LB times C of LB plus MW and CW is equal to this whole component. We can just rewrite that. Don't have to change that. LB TI plus MW CW and TIW. Now, what we can now do is we can take the component in the bracket from the equation and take it to the other side, which will isolate the T final. This is what we're looking for. So we'll get that LB TI of LB plus MW CW TIW over, you have M of LB times C of LB plus M of water times C of water. So this is now the equation with all the variables in place. We haven't plugged in any values till now. Now this tells us to figure out the final temperature, we just now have to plug in all the values that we had in the question. So now I'm going to plug in all the values. Okay, so this is the preferred way of doing it. If you are good with algebra, you can do it this way. And if you are not, then use that highlighted way. You can just plug in all the values right in the beginning and start solving for the answer. In terms of marks, you will get the same marks in both cases. But if you make a mistake in the calculation, it is much easier to see or fix the numbers. So if you put in a wrong number by mistake, if you have the equation, it is easier to just change the variables, change the numbers, and get a new answer. So let's plug in the values. Mass of the lead ball was 235 grams. Specific heat capacity was 0.13 joules per gram degrees Celsius, times initial temperature was 84.4, plus mass of water was 178 grams. Specific heat capacity was 4.18 joules per gram degrees Celsius, and the temperature initial was 20.5 degrees Celsius. That is all the values that we have on top. And the, again, mass of the lead ball was 235 grams, times the specific heat capacity of the lead ball was 0.13 joules per gram degrees Celsius, plus we have a mass of water, which is 178 grams, times the specific heat capacity of water, which is 4.18 joules per gram degrees Celsius. Now we have plugged in all the values, And now we just have to solve on the calculator to get the final answer. So I'm going to get my calculator here and clear everything. Starting from that, we have bracket 235 times 0.13 times 84.4 plus 178 times 4.18 times 20.5. I'm going to close the bracket, divide by whole thing, bracket 235 times 0.13 plus 178 times 4.18. So I'm just putting all of that information into the calculator at the same time, and I get an answer of 23.02. 3006 degrees Celsius as the final temperature of both the solutions, or of ball and the water. Okay, so that's the final temperature I'm getting. And again, looking at significant figures, we should have, since the two decimal places here, most of the work was 2 decimal places, significant figures, again, I'm not checking there, so it should be 23.0 degrees Celsius. I'm assuming it should be 23.0 degrees Celsius. I haven't kept track of all the significant figures here, but I'm assuming it's going to be 1 decimal place here, or 3 significant figures. So 23.0 degrees Celsius would be the final answer for the final temperature of this ball and the solution, the water.